Hello. Guess what? I was starting to write this out ahead of time, and then I thought, well, maybe you want to join me for this part of it, where I'm getting our balanced chemical equation written out here. Alright, so we are looking at stoichiometry in this video. It's a couple different types of stoichiometry problems. And the very first thing we always need to start with is a balanced chemical equation. So this one you can cross-check, make sure that there's mass balance on both sides of all the atoms that are there. But really, the take-home that I really want you to see with this balanced chemical equation is that there is a very specific mole ratio that has been given to us if we are given a balanced chemical equation. So what we have here, this mole ratio, is that we want to look at the stoichiometric coefficients. And while we can think of this as 3 sulfur atoms, 2 water molecules, like that, we really want to work with moles. And the reason for this is we live in a macroscopic world. We need to be able to see things. We need to be able to measure things. And the only way we can do that is if we have a large number of them. And since a mole is 6.022 times 10 to the 23rd of something, that means that we're going to be working with moles a lot more than individual atoms. So this mole ratio that we're working with is hearkening back to these stoichiometric ratios given here in the balanced chemical equation, where we're looking at a ratio of 3 to 2 to 2 to 1. And by the way, if there's nothing there, it is an implied 1. So we will be thinking about all of these in terms of these mole ratios. So here's an example of a kind of question that you might be asked with this type of problem. And let's just start out thinking about just moles. So here's a question. How many moles? So here's our question. How many moles of our H2S, our dihydrogen sulfide here, will be formed if this number of moles of sulfur is reacted completely with the water that's there. So this equation, by the way, this chemical equation, this is depicting essentially what would happen if you had elemental sulfur sitting out in a humid environment where you had gaseous water. And you would expect to get these two products. I did want to mention something to those of you who know a little bit more about sulfur. Elemental sulfur exists in molecules. That's a cluster of 8 of them. So this is simplified down to just assume that there's just one sulfur at a time. We're going to be looking at it that way. And that's okay to do that, because we could, if we had an 8 there, we would have a balanced chemical equation that would essentially be 8 times all these numbers. So, given this equation as it is, given this question, we want to start with what we know, what we've been given. And if you've seen my short video about if you're stuck on stoichiometry problems, when in doubt, calculate moles. Well, here we have been given moles for our sulfur. But we are going to be calculating moles of our H2S. But let's start with what we know, what we've been given. We know we have this many moles of sulfur. And our target is how many moles of the H2S. And here is where we use our molar ratio. Our ratio of how many moles of sulfur to moles of dihydrogen sulfide. We know moles of sulfur, but we want to convert out of that. So we want that to cancel out, so that's going to be in the denominator. And from this molar ratio, we know that there are 3 moles of sulfur for every 2 moles of the hydrogen sulfide, or dihydrogen sulfide. So this value we multiply by 2 and divide by 3, and that gives us a result. So this example here, this is portraying the main idea of mole ratios in balanced chemical equations. But the issue here with reality or with practicality is that if we look at this 0.334 moles of sulfur, how much is that really? What does that look like? Do we have a molometer that measures moles? No, we do not. But we do have things like balances that can measure grams. We have ways to measure volume and things like that. So from a practical standpoint, we want to know, what is the mass that we're looking at? So let's get an idea. What is the mass of this? Let's ask this other question. And this is where we would need a little bit more information. What do we need? If we want to go from moles to grams, we need the atomic weight, or the atomic mass of sulfur. We can get this directly from the periodic table. So we pull out our periodic table. I'm going to rewrite this so we can do our conversion. And the atomic mass, if we have 4 significant figures of sulfur, is 32.07 grams per mole. Depending on your periodic table, you might get more significant figures than that. And that's totally fine. Okay. So here we're converting moles to grams. So we want to use, notice I'm writing out this ratio ahead of time. We want to use the atomic mass as a ratio. This many grams per 1 mole of sulfur. So, since we're converting to grams, we'll have grams on top per. This is sulfur. You don't necessarily need to include that since we're talking about sulfur, but in any case, we can now multiply to get our value. And since we have 3 significant figures here, I'm just going to keep 3 significant figures here. This corresponds to 10.7 grams of sulfur. So this is something you can actually somewhat envision. Even if you're not used to measuring things in grams, you can imagine, okay, I can probably see that. I could probably measure that on a balance. It gives you a better idea of the amount that you're working with. We could do the same thing with the H2S as well, this amount. So just to give you an idea, what would that amount be if you have 0.223? Now what do you need? You need the molecular mass of H2S. I'm going to give that to you. And it is 34.082 grams per mole. This is 7.60 grams H2S. So once again, gives you an idea of the amount we're looking at in grams. Since this is a gas, it's probably more convenient to measure what the volume of this gas would be. And that's something you can do once you learn about the ideal gas laws and use the ideal gas law equation. But for now, we're just talking about moles and grams, so that works well there. Okay, so here is our first example of stoichiometry. But I want to do another one, because it's always good to start with one that is given the mass and then ultimately get the mass. Here I really just wanted to focus on moles and show you the idea of the mole ratio. Okay. So I'll get my notes. Get another piece of paper. So once again, we're going to start out with a balanced chemical equation. Alright, in this case, we're looking at elemental aluminum that is reacting with chromium 3 oxide under very high temperatures. So sometimes we show heat over the arrow. This means heat, high temperatures. We get this redox reaction happening. If you haven't learned about redox yet, don't worry about it, because we're just going to focus on the stoichiometry aspect of this problem. We get aluminum oxide and chromium. Okay. So here is our question based on this balanced chemical equation. This is asking, we're going to be thinking about this in terms of getting big amounts. So we're going to ask how many kilograms of aluminum that's supposed to be an N. You know what I mean. Okay. So here, imagine that you had 10.0 kilograms of this chromium 3 oxide. And you're trying to figure out, all right, I want to carry out this reaction. And this is, by the way, one of the ways you can produce pure chromium metal that's used. So imagine you're trying to figure out, all right, how much aluminum do I need for this? So, stoichiometry problems. First off, we need balanced chemical equation. We've been given that. But also, we will need a few other things. Usually, we'll be given the molecular mass of, or formula mass of chromium oxide. Oops, I forgot the 2, sorry. Chromium 3 oxide is 152 grams per mole. And we can also check on the periodic table and get the atomic mass of aluminum. 26.98 grams per mole. These will both come in very handy. Okay, so we start out with what we know. We have been given the mass of chromium 3 oxide. And ultimately, where we want to end up is with mass of aluminum. Alright, so this is the direction we're headed, right? But we need to do a couple steps in here, and that is when we're looking at balanced chemical equations, we can't go directly mass to mass. We've got to think about the mole ratios between them. So we've got to convert from mass of the chromium 3 oxide to moles. then that allows us to go to moles of aluminum with our mole ratio from the stoichiometric ratio. Then we can get our mass of aluminum. So now we can set this whole thing up, now that we know where we're started, where we're headed, and what we need to do in between. So since we are given the value in kilograms, I would suggest first taking a moment to convert kilograms to grams. Okay. And remembering we have our 3 sig figs here. So that gives us a starting point to carry out our full calculation. Okay, so here we are. It's 10 to the 4th grams of chromium peroxide. And now we need to convert to moles. Remember that? When in doubt, calculate moles, right? Here's our formula mass for chromium peroxide, 152.00 grams per mole. We are converting out of grams into moles. So if we want grams to cancel out, they've got to be down here. So again, think of your formula mass or molecular mass as a ratio. 152.00 grams of the chromium 3 oxide to moles. Then this is the point when you can convert from moles of chromium peroxide to moles of aluminum. Moles of the chromium peroxide are up here, so we want those to be down here. And we check back at the stoichiometric coefficient. There isn't one, so that implies 1, right? And aluminum, there are 2. So down here, for every 1 mole, chromium peroxide, 2 moles of aluminum. So let's see, how far along are we? We have converted grams to moles of chromium peroxide. We have now converted moles of chromium peroxide to moles of aluminum, but ultimately we want to know the mass of aluminum. So this is where we bring in the atomic mass. 26.98. Grams will be in the numerator, moles in the denominator, so that we make sure that moles cancel. Okay, moles. This is of our aluminum. I'll put aluminum there. Okay, so now moles. Ultimately, we'll get grams here. The question does ask for kilograms, but we can do that conversion at the end. Let's carry this out with our calculator. This mass will divide by 152.00. We will multiply by 2 and then multiply by 26.98. Okay, and what we get here is 3. 3.55 times 10 to the third grams of aluminum. It's almost on the edge there. Okay. And as I said, we want to make sure we convert to kilograms. So why don't we just do that? Scooch this all the way over and do one last conversion. So we're converting to kilograms. So here we'll put 10 to the third grams per kilogram. 3.55 kilograms of aluminum metal. There is our final result. Well, I hope these 2 examples were really helpful. And as always, I invite you to send me messages with your requests for any of the topics in chemistry that would be helpful for you. So don't hesitate to do that. You can put that in the comments. And not only do I invite you to give requests, but I also invite you to subscribe and to be part of our community here and to share this channel with anyone that you think might benefit from it, from learning chemistry in a really calm, relaxed, non-stressful way. We have enough stress in our lives, right? And especially if learning chemistry brings you anxiety or anything else, it's time to let go of that. And I'm here to help you do that. Alright, so thank you. Thank you for joining me as always. And I will see you again very